Hi everybody, this is Mr. Zarzak, and in this screencast I'll be working some example projectile problems. Okay, so let's jump right in, or in this case, fall right in. It says here a cliff diver falls from the cliff towards the water 30 meters below. How long does it take her to reach the water? Alright, so the key word here is that she falls. Okay, so this is essentially a freefall problem. Since it's a freefall problem, alright, what we can assume is that the acceleration is that due to gravity, and for all these problems today, I'm going to use 10 meters per second squared for gravity. The other piece of information that's given is that the water is 30 meters below here. Alright, so we've got some information about the distance. So to solve this, I'm going to use g equals VIT plus 1/2 AT squared. Now, you'll see in a little bit here, we'll be working problems in 2 dimensions. So to make this a little easier, or to set us up for later, I should say, alright, I'm going to add that all this information that I'm using is in the y direction, is vertical direction up and down. Okay, so that means that anything that's a vector, I'm just going to add a little subscript of y. So distance y, initial velocity y, acceleration y. Alright, now since she falls, there is no initial velocity, so that's kind of nice. So if this initial velocity is equal to 0, this entire first term in ultra omega 2 just cancels out, and I'm left with the simplified version of this. This dy is equal to 1/2 times ay times t squared. Alright, and since it says here, how long does it take for her to reach the water, what I'm really interested in is the time. So I'm going to go ahead and rearrange this algebraically to solve for time. So first I'm going to multiply both sides of the equation by 2. I'm going to rewrite 2 dy is equal to ay t squared. Then I'm going to divide out that ay, and that factors out there. Get a little bit more space here. I'm going to rewrite again. So I've got 2 dy over ay is equal to t squared. And then all I need to do is take the square root of both sides. And I'm left with this relation of the time to fall down this 30 meters is equal to the square root of 2 times dy over ay. Now I'm ready to sub in some numbers. Okay, I can choose whichever direction I want to be the positive direction. Since both the acceleration of gravity and the distance she falls are both down, I think it's way more convenient to make it down the positive direction. Okay, if you're more comfortable with making up the positive direction, go ahead, but you'll need to sub in negative numbers for both dy and ay. So just plugging and chugging. 2 times 30 meters divided by 10 meters per second squared. I would take that and throw that in my calculator, which I've already done, and you should get about 2.5 seconds. Okay, so now we're going to add to our problem. This time we're going to have our cliff diver jump forward at a velocity of 15 meters per second. We're going to ask, does this affect the time for her to fall? No. The idea here is that she just jumps forward. Okay, she's going to jump from the cliff with some initial horizontal velocity, so I'm going to call that Vx. Okay, the deal is that since she's just jumping forward, her initial vertical velocity starts off as 0. Now it's not going to stay that way for long because, well, gravity is going to cause her to accelerate as she falls, but to begin with, she's only got horizontal velocity. And that horizontal velocity is given as 15 meters per second. Alright, because there's no initial vertical motion, the time that she's going to be in the air for is still going to be that same 2.5 seconds. So let's write that down because that's pretty important. 2.5 seconds. So I'm just going to add a bit more to our picture here. So she jumps from the cliff. Here's that vertical displacement, or also known as the height of the cliff. That's that 30 meters and we call that dy. Okay, and it says how far away from the cliff does the diver land. All right, so I'm going to map out this distance, and I can see just a little hint of water here, and I'm going to assume that she makes it. Okay, we'll stay very positive with this problem. So what we're really looking for here is what's called dx. There we go. All right, so now she's actually going to move along this little like parabolic trajectory over here. Okay, it's not a very good parabola, but you get the point. All right, so she's going to arc through the air like that. All right, but trying to measure that arc distance doesn't really do much for us. All right, so what we do is we stick to things that we can measure and things that we can measure very easily, which are the height of the dy and the dx, which we can also call the range of the projectile. In order to calculate this, we again turn to ultra mega 2, d equals vi t plus 1/2 at squared. All right, now this time we're looking horizontally since we're looking for this horizontal distance. So I'm going to call it dx, vx. And the important thing here is that the acceleration horizontal, well, that's 0 because the only acceleration in this problem is, well, gravity. There is no horizontal acceleration. And so this entire second term just cancels right out. And we're left with the horizontal distance is just equal to this horizontal velocity times the time. All right, because there's no acceleration left to right in the problem, whatever speed we start off with moving horizontally remains that same speed the entire time we're in the air. So that Vx is going to be 15 meters per second for the entirety of the trip. So easy calculation, dx is equal to 15 meters per second times the time of 2.5 seconds. Throw that in a calculator, and you will get 37.5 meters. And this problem is done. Okay, so here's a little bit more complicated problem. It says the kicker kicks the ball at 25 meters per second at an angle of 35 degrees above the horizontal. If the goal is 2.4 meters tall, how far away is the kicker if the ball just hits the top of the crossbar? All right, so for these kind of problems that involve vector at some angle, all right, the first thing that we need to do is we need to take that vector and break it into components. We can't do anything else in terms of physics until we do that. All right, so I'm going to go ahead and draw a little picture here of the velocity vector for the kick. So that's v equals 25 meters per second. All right, and it says that this is at an angle of 35 degrees above the horizontal. So I'm just going to draw a little horizontal line, and I'm going to label my theta, and that is 35 degrees. All right, now this kick goes up and to the right, and so it has components go up and to the right. So I'm just going to go ahead and draw in my components here and here, and this is Vy, and this is Vx. All right, for Vy, okay, if I think about the SOHCAHTOA triangle, all right, the v, the 25 meters per second, that would be the hypotenuse. Given where the angle is, the Vy, that would be the opposite. So the trig function that relates v and Vy is the sine function. So I say Vy equals v times sine of theta. Vy equals 25 meters per second times sine of 35 degrees. Go to my calculator, crunch that out, you'll find 14.334 meters per second. All right, I'm going to do the same thing for the horizontal component. All right, the v, the 25 meters per second, is the hypotenuse of my triangle. The Vx, given where theta is in that corner, that would be the adjacent part of the triangle. So the trig function that's going to relate together Vx and v will be the cosine function. So Vx is equal to v times cosine of theta. Vx is equal to 25 meters per second times cosine of 35 degrees. Throw that in a calculator, and we will find Vx is 20.489 meters per second. All right. Once I have these components, I'm actually going to take and I'm going to make a whole new picture to kind of help me work this through. Okay, so I've got a new page so I can draw a new picture of what's going on in this problem. All right, so I'm just going to add in my Vy is equal to that 14.334 meters per second. I'm going to add in my Vx. Vx equals 20.489. Okay, and I know the way I've got them drawn looks a little weird. All right, but I've done this intentionally for two reasons. Okay, one, I'm not going to draw in the angled vector. The 25 meters per second at the angle of 35 degrees is now gone. All right, I'm not going to use it anymore in the problem. The number one mistake with these kind of problems is trying to use it for anything after we've broken it up into components. All right, I've got my vectors drawn like this so that I can show the approximate path of the projectile originating from this point to where the ball is kicked, okay, over to this point, to this distance of 2.4 meters, which is the distance, is the height of the goal. So this is my dy, and that equals 2.4 meters. Okay, so this is the picture that's going to help me out, all right, in terms of solving this problem. All right, what we're asked to find is how far away is the kicker. So what we're looking for here is dx. That's our unknown. Okay, and like so often with these physics problems, to get what we really want, which is this dx, we're going to have to solve for some intermediaries. And by that, I mean we're going to need to solve for the time it takes the ball to reach the goalpost. All right. In order to do this, we actually need to look in the vertical dimension. We need to look in the y direction first. The reason being is, well, the whole reason that this ball hits the goalpost is because gravity is what's causing it to arc through the air. So if I look vertically, if I look in that y dimension, okay, I'm going to apply ultra mega to dy is equal to v it plus 1/2 ay t squared. All right, subbing in this vertical distance dy, well, that's the height of the goalpost. That's the 2.4 meters. So 2.4 meters is equal to my initial vertical velocity. That's the Vy component that I found before. That's that 14.334 meters per second times the time plus 1/2 times the acceleration in the y direction, which that's gravity. That's your -10 meters per second squared. All this times the time squared. Now just to clean this up a little bit, 2.4 is equal to 14.334 times the time plus -4.9 times the time squared. Okay, and a little bit of rearranging. I think I'm just going to move the 2.4 over and have this equal to 0, so I wind up with 0 equals -4.9 t squared plus 14.334 times t minus 2.4. And as I'm sure you've already noticed, this is a quadratic. Okay, so I'm just going to go and circle my coefficients. A, B, C. All right, so go ahead and apply the quadratic equation, which, if you don't remember, will give us answers for time. It's negative b plus or minus square root b squared minus 4 AC, all that quantity over 2A. All right, so I'll go ahead and let you do that. When you do apply it, you should find two values for time, and in this case, both the times will be positive. So you'll get this 0.1783 seconds and 2.747 seconds. So with both of them being positive, the question becomes, all right, well, which one's the correct value? Well, here's where we got to go back to that picture. Okay, we had the vertical velocity, the horizontal velocity. Okay, and then we arc through the air, something like this. All right, and then we had our goal post at 2.4 meters in height. All right, so the trick is that, well, this distance here is 2.4 meters up, but it's not the only time the ball passes that 2.4 meters. But look here, so if I just kind of trace this over, like, look, the ball actually hit that 2.4 meters as it moves up and on its way down. Since our goalpost is where the ball is on its way down, we need this 2.74 seconds of time, or 2.747 seconds of time. That's what's going to give us the answer we need for this problem. So let's go ahead and finish it. We want to know how far away the kicker was from the goal, so that we're looking for that value that we call dx. All right, if I take and I apply ultra mega mega equation 2, VI t plus 1/2 a t squared. All right, just like with our cliff diver problem, or with any projectile problem for that matter, there is no horizontal acceleration. The only acceleration for an object once it's in the air for a projectile is gravity. And so this entire term just cancels out, because if ax equals 0, doesn't matter how much time passes, that term is always equal to 0. All right, so take my dx is equal to Vx, which is that horizontal component of velocity that we found all the way back at the beginning of the problem. It was that 20.489 meters per second times this time of 2.747 seconds. Throw that in your calculator and get a distance of 56.283 meters. The kicker is 56.283 meters from the goal. Okay, so these kind of problems obviously require a little bit of practice. All right, so I've got another problem here for us to work. We're actually going to let you guys work it. I'll give you the answer and some tips along the way and see if you can work this out. So what we've got here is we've got a student who's throwing a ball, and the ball is going to be tossed off this cliff so that it arcs down and goes right into this net down here. All right, so this is what's the only difference in this setup from the soccer problem is this, well, this location here of the ball, that's our 0 location. All right, if it's going to make it through into the net, the ball actually needs to go down so that our dy is down. That means it's going to have a negative value. So if we say that the hoop is 2.4 meters below the top of the cliff, all right, and that the ball is thrown at a speed of 25 meters per second at an angle of 35 degrees above the horizontal, the two questions I have for you are, 1, how much time does it take for the ball to go from the student into the net? And then 2, how far away is the net from the student horizontally. Since we already got the we've got the vertical distance, now find the horizontal distance. When you're solving this, just remember that this dy here is negative 2.4 meters, okay, because the ball is going to land 2.4 meters below from where it was thrown. I'll have the answers on the next slide, but I would say that you should pause it at this point and try to work the problem before you peek at the answers. All right? Feel free to work with your team, and good luck. Okay, well, here's the answers. Hopefully you didn't peek ahead and you tried this for yourself before you looked. And even more importantly, hopefully you got 3.08 seconds for the time and 63.1 meters for that horizontal distance. This is Mr. Zarzak saying thanks for watching. We'll see you in class.